In this lecture, we would try to derive the expression for pitch factor of a coil, of a corded coil. So, what is the meaning of this term pitch factor, or what is the meaning of corded coil? We will find it out in this particular lecture. So, for finding out this, I have taken this particular example where I have shown one coil. So, first of all, you can see here that this coil, let's name the coil. Let's say this is your coil side A and this is your coil side A dash. So you can see that coil AA dash is a full pitch coil. Now, in which way, in which manner we have detected or we have concluded that coil AA dash is a full pitch coil? The answer is very simple. You see, the two sides of the coil AA dash, the two sides of the coil AA dash are such that coil side A is at center of north pole, is under center of north pole, and coil side A dash is under center of south pole. So this is one of the simplest technique of locating or finding out whether the coil is full pitch or not. That if it is a full pitch coil, one coil side will be at the center of north pole, other coil side for the same coil will be under the center of south pole, or maybe south pole and north pole, vice versa. But both the coil sides for the same coil, they should be under the center of north and south pole. So that will be termed as full pitch coil. Now, what is the meaning of short pitch coil? Short pitch coil can be this one. Let me show you. Over here you can see this arrangement of coil. Let's say this is your coil side A, this is your coil side A dash. So this over here, coil A dash is said to be a short pitch coil. Coil A dash is said to be a short pitch coil. Short pitched coil. Now, what is the meaning of this word short pitched coil? Short pitched coil means coil span is less than 180 degree electrical. So here you can say short pitch coil means coil span is less than 180 degree electrical. Now if you notice, I have taken the case of a two-pole machine. So since I have taken the case of a two-pole machine, we know that theta electrical and mechanical are same. So let me write that for a two-pole machine, as shown above, theta electrical and mechanical are same. Theta electrical and theta mechanical are same. Since we know that theta electrical equals to P by 2 theta mechanical. So if you just want to quantize that what is the angle of short pitching, so let's say we can elaborate in this way. This angle is say epsilon. Okay, so the angle of short pitching the angle of short pitching is epsilon degree. That means the coil is short pitch by that. So you can say that the span of the coil, the span of the coil, the span of the coil is 180 degree, but it is not 180 degree, it is less than, it has been short pitch by how many degrees? Epsilon degree. So this is the span of the coil, 180 degree minus epsilon. Now, why we actually short pitch a coil? There are different reasons, variety of reasons. Mainly we short pitch a coil to eliminate some harmonics, because we know that the actual distribution of MMF in the air gap is non-sinusoidal. It is somewhat like trapezoidal. So due to that non-sinusoidal distribution of MMF in the air gap, what happens? The harmonic MMF can be said to be present. I mean to say, why or from where at all the harmonic MMF is coming. Let me give you some idea from where and how I am saying that harmonic MMF is coming. If I just draw a thing like this, let me draw it like this, or let me better copy from there, that will be better. Let me copy it from here. So you take the case of this one. So strictly speaking, what is the distribution of MMF over the rotor surface? MMF or flux density, whatever you call. Let me show it over here. The actual distribution of B is like this. Let's say this is 1, 2, 3, 4, 5, 6. One, two, three, four. 1, 2, 3, 4. So I just want you to find it out. It is actually not drawn correctly. Let me correct it. The peak should be same for the positive and negative portion. Peak has to be same. So let me draw it. Let me draw it correctly. So let's say this portion is the MMF, okay, magnetomotive force, or you can always replace MMF by B, that is the magnetic flux density. So this is the actual distribution. This portion is this portion is the rotor surface. This portion is the distance over rotor surface. Distance. This is your distance along rotor surface. So this is the actual distribution. This is the actual distribution of magnetomotive force, or you can say also, you can actually replace MMF by flux density B. Okay, it's not a big deal You can easily do some scaling along the y-axis, and with that scaling you can replace MMF by B. So this is the actual distribution of B. So you can think that you can go for some Fourier series expansion, so that the fundamental component will look like this. I am trying to draw one sinusoidal wave. So this is the fundamental component of MMF. Basically the idea of the Fourier series is that Fourier series is that we will replace this trapezoidal MMF by large number of sine waves. I am only indicating one sine wave. This one sine wave is the fundamental component. There will be harmonic components also. So this is the fundamental component. This is the fundamental component. There can be harmonic components. You can have harmonic components. If I just want to indicate it, I am not drawing it to scale. I am just trying to give you some idea. So let's say I am drawing it like this. So this thing is your, say, harmonic component. This thing is your harmonic component. This thing is your harmonic component. So it is not like that you will have only one harmonic component. No, there will be theoretically infinite number of harmonic components, but theoretically we are not going to deal. Maybe up to 7th or 11th or 13th harmonic is present. Higher order than that also is present, but the magnitude of that is going to become very negligible. So we say this one thing in particular, that as the order of harmonics, increases, as the order of harmonics increases, its effect is less and less. As the order is increasing, as the order of harmonic is increasing, the effect is becoming less and less. That is what is true. So we see that besides this fundamental component, there are lots of harmonic components. So one reason for short pitching a coil can be this, that we want to eliminate some harmonic EMF. Okay, so elimination of harmonic EMF can be one of the reason. Number one is your, what can be the reason for short pitching a coil? Reason for short pitching a coil. Short pitching a coil. Number one is elimination of harmonic EMF. Elimination of harmonic EMF induced in the coil. Now there is one interesting fact here, is that we can eliminate only one harmonic EMF by short pitching a coil. It is not like that we can eliminate all the harmonic EMF. So usually what is done, we eliminate the lower order harmonic EMF, because that will be more prominent. As I have said earlier, as the order of the harmonic is going to increase. For example, if I compare, 11th order harmonic will be more prominent. The effect, what I want to say, the effect of 11th order harmonic will be more prominent compared to 13th order harmonic. Likewise, effect of 9th order harmonic will be more prominent compared to 11th order harmonic. So as the order of the harmonic goes on increasing, the effect of that harmonic becomes somewhat negligible. You can ignore. So when we are going for short pitching a coil, so as to eliminate the harmonic EMF, we usually eliminate the harmonic EMF corresponding to a lower order harmonic, maybe third harmonic or third or fifth harmonic, like that. Okay. So what is the advantage of going for short pitching a coil? If you are short pitching a coil, then the copper is required is less. Let me show you here. If I just again bring on the grid line so that we can compare it better. Let's say I am drawing a coil here. Say this coil is a full pitch coil. This coil is a full pitch coil. Now short pitch coil will look like how it will look like. Short pitch coil will look like this. Short pitch coil will look like this. So this thing is your short pitched coil and this thing is your full pitched coil. Let me zoom it for you so that it is better view. Now you see. So this black one is the span representing for a full pitch coil. Okay, black one is for a span representing for a full pitch coil. Full pitch coil. And this red one is for your short pitched coil. Short pitched coil. So what do you find? Length is shorter. Length is shorter or short pitch coil. Length is shorter for this coil, which is shown by red, and over here length is longer. Length is longer. Length is longer. So one of the advantage of short pitching a coil is that you are having some saving in copper, because the length is becoming shorter for short pitched coil, so the volume of copper required will be less compared to the full pitch coil. Okay, so this is one thing you can say, but there is a disadvantage also. What kind of disadvantage? The disadvantage is that reduction in the induced EMF. So we are basically trying to find that that due to short pitching of coil there will be reduction in induced EMF. So if I say that let's say this is my full pitching coil, and if you want to short pitch it by this, so short pitching a coil, it will look like this. It will look like this, short pitching a coil, and this is the angle of short pitching, epsilon. So due to the short pitching of coil, there will be reduction in the induced EMF. Due to short pitching, of coil, there is a reduction in induced EMF. There is a reduction in induced EMF. And pitch factor will let you know, the reduction in the induced EMF due to short pitching of coil. So we can say induced EMF with short pitched coil, divided by induced EMF with full pitch coil, divided by induced EMF with full pitch coil. So pitch factor is it's a number, because you can see it's a ratio. ratio of EMF, so there is no dimension, it's a number. So pitch factor will give you an idea about the reduction in the induced EMF in a coil due to short pitching. Because you see, pitch factor is given by induced EMF with short pitch coil divided by induced EMF with full pitch coil. So you can take this figure as the reference. When coil A dash is your full pitch coil, you find the induced EMF, you write that in the denominator, and when coil A dash is short pitched, then you write that induced EMF with short pitch coil in the numerator. So that ratio will give you the pitch factor. So obviously this particular angle will be how much? It will be 180 degree minus epsilon. 180 degree minus epsilon. Let me write it another way. This is your 180 degree minus epsilon. Okay. So now how to find it? Now before I start with, I would like to say that you can see here the distribution of magnetic flux density over the rotor surface is assumed to be sinusoidal, and the reason I have said earlier that the actual distribution is like this, trapezoidal over the rotor surface, but we are applying Fourier series and we are only taking the fundamental component. So that's why we are saying it is sinusoidal distribution like this. So right now you can see how the position, when the coil is full pitch coil, how the coils are there actually. You can see it here. This is the position of the coil. Let me show you. This is a coil side A, this is a coil side A dash. When it is a full pitch coil, when it's a full pitch coil. But when it is a short pitch coil, it will be moved to another position like this. So in that case, it will be like this. So that way you can find it out. Let me just do one thing. Let me draw it twice. One for full pitch coil, another for short pitch coil. That will be, it will be better. So this is my representation over here, and I will be showing this thing twice. One with full pitch coil, another with short pitch coil. So this is with full pitch coil. The coil position, you can see it over here, A and A dash, they are under the center of say north pole and south pole, you can see it. And if it is short pitch, how it will look like. If it is short pitch, there will be one small difference. What is that small difference? I'll let you show you. This won't be here. It will be slightly away from the center of the south pole. So exactly speaking, it will be somewhat away from the peak of the south pole. So it will be here. So this is your coil side, say A dash, this is your coil side A dash. So this span is actually less than that. Okay, so this span would have been 180 degree. This span would have been 180 degree, but it is actually short pitched by this angle. What is this short pitching angle? This short pitching angle is epsilon. So obviously this one is, how much is this span? It is 180 degree minus epsilon. But here you can see it's a full pitch coil, no doubt about that. over here the coil is a full pitch coil, so this thing is your 180 degree. It's a full pitch coil. This thing is your 180 degree. And you can see this is the center of the north pole, this is the center of the south pole. Again this is the center of the south pole, and this one is the center of the north pole. So it is slightly away from that, like that. Now we need to derive some mathematical expression. We have tried to understand it from the point of view of qualitative point of view. So this is your this thing is your short pitch coil. If I write like that, this thing is your short pitched coil. Short pitched coil. This thing is your the upper portion is a full pitch coil. This one. This one is a full pitch coil. This thing is a full pitch coil. Now we see that the distribution of flux density over the rotor surface is sinusoidal, the way it is shown here. So induced EMF in the coil A dash will be also sinusoidal. Okay. So we can represent the induced EMF in the coil by phasors. So we can write like this: distribution of B, that means your flux density over the rotor surface, over the rotor surface is sinusoidal. Distribution of B over the rotor surface is sinusoidal. Hence induced EMF in coil A dash is sinusoidal. And therefore it can be represented by phasor, and therefore it can be represented by phasor. 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 So we will do that only. So if it is a full pitch coil, how we can represent it by a phasor? We will see. If it's a full pitch coil, and if it's a short pitch coil, how we will represent? We will see it. So if it's a full pitch coil, what is the thing we have shown it for full pitch coil? This is what we have shown for the full pitch coil. This is a full pitch coil. So how to represent it by phasor? We will represent it by these two phasors. Let's say A dash is not here. Okay, this is a full pitch coil. This thing is a full pitch coil, so A dash is not here, as if A dash is not here, so it's a full pitch coil. So this angle is obviously your 180 degree, and if I represent it by phasor, it will be looking like this. This is one phasor, and this is your another phasor, let's say. And if I say in terms of coil, if it is in terms of coil, it will look like this. So the induced EMF in these two coil sides A and A dash, this is a coil side A and A dash. Let's say coil side A is under north pole, coil side A dash is under south pole. So polarity will be like this. If this is plus minus, this will be also, it should be opposite of that. So it should be your minus plus. And the north pole, if it is like this, and the south pole, it will be opposite polarity. Now if you take the KVL, because we were interested in knowing the induced EMF here, so voltage across this terminal, voltage across this terminal, what is the voltage across this terminal? It will be simply, if I just name it here, let's say this is point O, this is A, let me write capital A, O, A, B. So voltage across this will be how much? Now what is OA? OA is the voltage in coil side say A. In coil side A, this is the voltage. What is OB? OB is the voltage in this coil side. So this is your OA, this thing is your OB. But what is the voltage across this terminal? What is the voltage across this terminal? The answer will be like this. The answer will be OA plus OB. So it will be OA plus OB. That means they have to be added together. Because when you are taking the KVL in the closed loop of the coil, the voltage are actually getting added up. So that's why we are adding OA and OB. We are adding OA and OB like this. So this is the voltage across the terminals. This one, OA plus OB. This is the voltage. This is the voltage. We are adding it. We are making the sum of this. We are adding it together. Okay, so this was for the full pitch coil. Now what about the short pitch coil? Short pitch coil is how we are going to find it. Let's see. Short pitch coil. So again I will try to copy this off. So now we will keep the short pitch version, and also we will take the short pitch version from this side on also. So this is a short pitch coil, and we will not keep the full pitch version now, right now in this case. So over here in this particular case, what you can find, how you are going to represent it by phasor, the way we have represented earlier. So over here now, the coil is short pitched by some angle epsilon. The coil is short pitched by some angle epsilon. So this is say under the center of the north pole, this one. But this is no longer at the center of south pole. South pole is here. The coil is actually short pitched by some angle. The coil is actually short pitched by some angle. So these will be all actually dotted. These are not. The coil is actually short pitched by some angle. What is that angle? That angle is epsilon. So in this case also, if you just find the polarity, what polarity we have seen? We have shown arbitrarily that under north pole if it is plus minus, under south pole it will be opposite, that means minus plus. So that polarity will remain same only, like that. This will be minus, this will be plus, this is plus minus, but the value will be different. Over here, let's say the value is EM, let's say value is EM for this one, this is the value EM, this is also magnitude wise, this is also EM, because both are under the peak. You can see both are under the peak of the north and south pole. So induced EMF will be maximum for both of them. We had here coil A, coil A dash, this is a coil A dash, this is a coil A. So both are having peak of the flux density, na? Both are having the peak of the flux density. This flux density was peak, it was BM, and it was also peak, negative peak. This was also BM. But now in the short pitch case, it is not like that. In the short pitch case, what will happen? In the short pitch case, you can see this will be your coil A, and over here you will have the coil A dash. Over here you will have the coil A dash. So now in this case, induced EMF is say EM, but in this case it is EM cos epsilon, EM cos epsilon degree. It is short pitch by epsilon degree. So now if I want to draw it in terms of phasor, how it will look like? Let's see. So this is your O, this is your A. Now what will be B? Where will be OB? Earlier it was both 180 degree apart. This was your 180 degree apart, this one. This thing was your 180 degree apart in the case of full pitch coil. But in the short pitch case, it won't be 180 degree apart. It will be less than 180 degree apart. So by how much less it will be? This will be now B, and this angle will be 180 degree minus epsilon degree. Okay. And this is the dotted portion. You can say this portion is the epsilon degree. So now what will be the voltage across these two terminals of the coil when they are short pitched? So we have to, let me just draw it over here. So we are drawing like this. Let's say this is O, this thing is OA, this thing is A, this point is O. Now we are actually going to reverse OB. Why we are going to reverse OB? Because if you recall, in the previous case also we have actually reversed OB. Let me show you. Over here we have reversed OB so that we can add them OA and OB together, because when we are taking the KVL sum inside the coil loop, they are getting added up. You take the KVL inside the, apply KVL for this loop, voltage is getting added up. Let me write it here. Apply KVL in this loop, voltage is getting added up, for two coil sides, A and A dash. That is the reason we are reversing it here. Okay. So by the same logic we have to reverse OB. So if you reverse OB, how it will look like? This portion is your OB, this portion is your OB. So we are actually reversing it. Okay, we have reversed OB. OB phasor is reversed. Why it is reversed? Because when we apply KVL in this loop, when we apply KVL in this loop, EMF of coil side A and A dash are added up, are getting added up. So that's why we are reversing it, okay, added up. So this point, let this point be called as C. Okay, so actually this OB is like this only. OB is like this only. This thing is OB, but it is actually reversed here. Okay, this thing is reversed here. So what is the voltage which is actually available across the terminals? So let me show you the voltage available across the terminals. So this OC is the voltage available across the terminals of the short pitch coil. So we can say that OC is the voltage across terminals of coil AA dash. So you see, right now, till now, whatever I am saying or discussing, these are actually qualitative, but it's not like that totally qualitative. We are moving towards some mathematical derivation, which will allow us to derive some expression for the reduction in the induced EMF in the coil due to short pitching. But right now, you can see that OC over here in the diagram, OC is the voltage across the terminals of coil AA dash. Of course, this coil is your short pitched coil. This coil is your short pitched coil. This thing is a short pitched coil. So now, how to find the expression? So let's say that OC is the voltage for this one, this coil, voltage across these coils. So we will again draw this in that way. Let me say, let me try to copy this. So this point is your C, as you have seen earlier. This point will be C. This point is C. Now I draw it once more separately. Okay. Let me draw it once more separately. So I am drawing it on a somewhat bigger scale, so that the things are visible that way. So this point is your point O, this point is your A, this is your C. And if you want to put the arrow markings, these are the arrow markings. Obviously, we have another thing like this, OB. This will be longer slightly. This thing is your OB. Now, sorry, what about this angle? This angle is your actually 180 degree, and this thing is your epsilon. This particular angle is your epsilon. So this angle will be 180 degree minus epsilon. Now let us drop a perpendicular from point A on OC. Okay. So this thing is your perpendicular bisector. This thing is your perpendicular bisector on OC. So this is the perpendicular bisector drawn perpendicular bisector drawn over OC. So this angle, if it is 180 minus epsilon, obviously this angle is also 180 minus epsilon. So this angle will be 90 degree minus epsilon. This will be 90 degree minus epsilon. Half of that. You can apply the school geometry which you have studied in your school for figuring it out. I am just giving you some helping drawing or diagram. You can see if this angle is epsilon, this angle is also how much? This angle is also epsilon. So this is 180 minus epsilon. This is the perpendicular bisector drawn. Let's name it. Let's say this is your this point is your D. So the AD is the perpendicular bisector. Now you can just take this triangle. Take this triangle ADO. So you are taking triangle ADO. Now you want to find what? You want to find this OD. Okay. So OD is what you want to find. So OD is the perpendicular. Let's say we are. If this is 90 minus epsilon, this angle is 90 degree definitely. This angle is 90 degree. So this angle is how much? It is not 90 minus epsilon. It will be 90 minus epsilon by 2. So this angle is epsilon by 2. Epsilon by 2. Because the perpendicular bisector will bisect this angle. Okay. Let me write. Perpendicular bisector AD will bisect angle, will bisect which angle? CAO. What is angle CAO? It is 180 degree minus epsilon degree. So if it is bisecting it, obviously angle DAO is nothing but 90 degree minus epsilon by 2. So from here we can say that OD by OA equals to cos of epsilon degree by 2. What is OD? I just want to take this as a OD is your base. OD is your base. What is OA? It is your hypotenuse. So that's why you get this. So from here only we get the thing that OD equals to OA into cos epsilon by 2. But what is OC? But we say that OC equals to how much? OC equals to twice of OD. OC equals to twice of OD. OC equals to twice of OD. So we can write this OD, instead of OD we can write OA into cos epsilon by 2. So this is OC. Now we are somewhat closer to the finding the pitch factor. How? If this would have been a full pitch coil, then the induced voltage across the coil would be 2 OA. Okay. But for short pitch coil it is OC as shown earlier. So pitch factor Kp equals to induced EMF with full pitch coil. Sorry, this term will be in the denominator. So induced EMF with full pitch coil, this thing will be in the denominator, and in the numerator induced EMF with full pitch coil. In the numerator you have induced EMF with short pitch coil, actually short pitch coil. So So what we have gathered till now by the discussion, induced EMF for short pitch coil is nothing but voltage phasor OC. OC we have seen, OC is the voltage. So OC will be in the numerator, and in the denominator we have what? Twice of OA, because we have seen earlier here OA plus OB, but OA and OB are equal, na? OA and OB are equal. OA equals to OB. So it is how much? It is twice of OA. So that is what we are going to write here, twice of OA. So it is your twice of OA. But what is OC? OC is your twice of OA into cos epsilon by 2 divided by twice of OA. Now it's anybody guess. 2A OA will cancel, it will be your cos epsilon by 2. So this particular expression cos epsilon by 2 is your pitch factor Kp. This thing is your pitch factor Kp. So with the help of this expression pitch factor, which is denoted by symbol Kp, which we have found as cos epsilon by 2, we can say that the factor by which induced EMF is reduced is given by cos epsilon by 2. Okay. So let me stop it over here for today.